Good evening, my friends. Myself, Dr. Sukhwinder Singh, Associate Professor in EN Department from Ajay Kumar Garg Engineering College, Ghaziabad. Today, I am going to discuss torque equation and performance characteristics of DC shunt motor and series motor. In this live section, we will discuss in detail how we can derive the torque equation of a DC motor, and after that, we will discuss performance characteristics one by one for each of the type. Let us start with the DC torque equation of DC motor. For the torque equation of DC motor, I will start with the voltage balance equation, because there are so many ways to obtain the torque equation of a DC motor. But in this session, I will discuss particularly easiest way to obtain the torque equation of a DC motor. In most of the examination point of particular questions, they ask for the torque equation of a DC motor. This is about 10 marks generally. For torque equation, I have chosen the separately excited DC motor. Let us suppose we have, this is particularly armature circuit for the separately excited DC motor, so that we can have the particular generalized equations for the DC motor. Here we have the DC supply for the armature circuit separately. You can see over here, this is VDC and this is the armature current. Okay, we know that RA is the armature resistance and back EMF is the EB. I will discuss in detail what is the significance of back EMF also, and separately we have the particularly field winding for this separately excited DC motor. In this case, I have a rheostat arrangement so as to control the current in the field winding like this, and then we have DC source, separate DC source in this also. This is VDC, this is for the field circuit, this is the rheostat, and with the rheostat I am going to control the field current of this field winding, and we have the R field RF. RF is the field resistance. Okay, now we have separate circuit for field circuit as well as armature circuit. आया कुछ आया सर आया हाँ. Just wait, sorry for the particular instruction. Now for the separate circuit of field and armature circuit, let me write the voltage balance equation like VDC. We have EB plus IA into RA. This is the voltage equation for the armature circuit. This is equation number 1. This is for armature circuit. Let me write armature circuit. Okay, next we have the field circuit, and for the field circuit, that is VDC1. For the separate source we have, that is given to be the IF into RH, whatever the rheostat resistance is connected in series with the field winding, and we have the field circuit resistance RF. And from here we can find what is the IF for the field circuit, that is VDC. This is the current in the field circuit, VDC1 divided by RH plus RF. So this is the field circuit voltage equation from where we have the field current. This is equation number 2, and from equation 1 we have armature current like VDC minus, this is particularly EB divided by IA into, sorry, here we have resistance Ra. Let me erase this one. This is resistance Ra we have. This is Ra. Okay, now you can see over here we have the armature current in this manner. Okay, and from the voltage equation, voltage equation of armature, multiply the same voltage, the same equation by a armature current Ia, so as to get the power equation or power equation. We are going to get the power equation like we have VDC into Ia, that is equals to EB into Ia plus Ia square into Ra, in this manner, because we know that this is particularly the loss. Okay, that is the, you can say, ohmic loss we have, and this is dissipated in the surrounding. And whatever the electrical input power we are giving to the armature, that is the electrical input power we are giving, and this is the EB. EB is the particularly back EMF, or you can say generated EMF, which is opposite to the supply voltage VDC, or in the opposite sign. That's why this back EMF has its own significance. It will regulate the current, and we know that the torque is directly proportional to the flux into Ia. That is the result of our particular equation, and that's why when the motor pick up the speed, then there will be a back EMF, and that back EMF is gonna control the current armature, and accordingly there will be control over the torque also. That's why this is the power. This is what power? This is the electromagnetic power. Electromagnetic power that is developed in the rotor circuit, in the rotor or armature circuit, rotor oblique armature. Okay, this is the armature circuit, and this is the power which is converted into mechanical power. This is the power, this is the electrical power which is converted into mechanical power. Okay, so this is the power EB into Ia, which is responsible for the mechanical power development, or we can correlate the equation of this electrical power with respect to the mechanical power. Mechanical power is evaluated or you can say equated as or equivalent to the omega into torque. Okay, let's go to the next slide. Then we are going to obtain the particular result of this torque equation. Now we know that the mechanical power developed is in equilibrium with the electromechanical power in the armature circuit. What is this mechanical power? This is omega into T, and this is equals to, here we have the particular electric power, that is EB into Ia, where EB is what? EB is only induced when there is a rotation of the armature, and it is equivalent to phi Z N P upon 60A, like this. Okay, where phi is the flux and P is the total number of pole. Phi is the flux per pole, P is the total number of pole, N is the speed in RPM. We have converted into RPS by dividing with the 60 factor, and then we have the A is the parallel path, and Z is the total number of the armature conductors. Okay, total number of armature conductors, and here we have T is given by EB into Ia divided by omega. Okay, where EB is equals to phi Z N P upon 60A, this is the formula for EB, and multiply by Ia armature current, and omega we know that we can convert into radians per second. 2 pi N is RPM divided by 60 becomes RPS. Now we have this omega angular speed, that is radians per second. Now what are the factor we can cancel out from here? What we have is torque comes out to be, this is the torque equation, phi, okay, Z, N is gonna be cancel out, okay, 60 is gonna be cancel out, divide by 2 pi as it is, 2 pi as it is, and then divide by A, that is the parallel path, and we have a particular number of poles as it is P, okay, phi Z into P multiply by IA. Okay, this is the particular expression for the torque. And what are the constant in this equation? What are the constant? We can equate those constant like this K. K is comes out to be Z into total number of poles of the machine divide by total parallel path, and also 2 pi we can also taken it in the constant term. That's why torque comes out to be K times what is flux of the air gap, and then we have armature current IA. This is our third equation, or this is known as the torque equation of DC motor. Okay, now you can see over here what we have is torque equation, and we can generally see torque is directly proportional to phi into IA in some of the books. So we can also represent in this form also, torque is directly proportional to phi into IA. This is the generalized equation of the particular motor. Okay, then if we come towards the speed equation, okay, this is the fourth equation we have, that is for torque equation, because after that we have to discuss about the performance characteristics of DC shunt and series motor. So these are the generalized relation, and in the shunt motor as well as the series motor we have to do some modifications in the parameters so as to get the particular desired performance from each of the motor. Now as we know that back EMF is represented by what? That is phi Z N P upon 60A. Okay, from this relation I can equate the particular, or you can determine the expression for the speed, that is given by EB, this is EB into 60 divide by this particular flux, and this factor is as it is, this is Z into P. As we know that again this factor is gonna be the constant term. Okay, this is the constant term. That's why we can have the particular speed equation like K1, that is EB divided by the flux, where K1 is given by your 60 by Z into P. So this is the constant term. Okay, and we can also write in generalized way speed is directly proportional to your particularly EB by phi. Or we know that from the voltage equation, from equation number 1 which we have discussed in the previous slide, that is the voltage balance equation. From that voltage balance equation what we have is this EB can be represented in the electrical circuit like VDC minus IA into RA, like this. Okay, that's why what I am going to do, I can represent this speed is directly proportional to this VDC minus IA into RA also. In this way also I can represent the speed. Okay, so this is your particular sixth equation. By following these equations of torque, speed and voltage balance equation as well as the armature current equation, we have the performance characteristics, okay, of each of the machine. Let me move towards the next slide. Before discussing about the performance characteristics of shunt and DC series motor, let's have a look on these applications of both the machines. Application of DC shunt motor. DC shunt motors are used where the constant speed is needed. Okay, because DC shunt motor have the property of speed regulation. under load conditions. So these motors are commonly used in the fixed speed applications. Next we have this type of motor is used in lathe machines, centrifugal pumps, fans, blowers, conveyors, lifts or weaving machines. Then we have spinning machines, etc. Then we have the application of DC series motor. DC series motors are used where high starting torque is needed. The motors are only used where variation in the machine speed is required, okay, or it is possible. Series motors are not suitable for the constant speed applications due to its performance characteristics. We will discuss it later. DC series motor is used in vacuum cleaners, then traction systems, sewing machines, then cranes, air compressor, etc. Now let's proceed for the performance characteristics of each of the type. Now, first of all, I'm going to discuss the DC shunt motor and its performance characteristics. When I'm talking about the performance characteristic, it means I'm going to draw the characteristics of DC shunt motor between the torque and torque versus armature current. This is the first performance characteristics. Second one is the speed versus armature current, and then third one is the speed versus torque characteristics. Okay, first of all, if we are going to discuss the DC shunt motor performance characteristics, I need to draw its circuit diagram. That is the must required thing for each of the machine. When we are discussing about any of the machine, we need to have its circuit diagram. Okay, first of all, I'm gonna draw the circuit diagram of DC shunt motor. In the DC shunt motor, we have the armature circuit like this. Okay, and then we have the field circuit. Field circuit has sufficient resistance, that is RF. When we talking about the speed control of DC shunt motor, then we have the particular another arrangement of rheostats, because we know that for the speed control method we have different aspects like armature control, okay, then field control. And for the armature control, we need to connect the rheostat in the circuit in the series to the armature circuit, and for the field control we have to connect the rheostat in the field circuit. Okay, armature control is generally used for the speed up to the rated speed, but the field control is employed when we need to have the speed above the rated speed, like that. Okay, now you can see over here we have the VDC, the source voltage is here, then we have this particular load current. For the DC shunt motor, this is your field current IF, and then we have the armature current. This is the armature current. Okay, now you can see over here again the voltage balance equation, balance equation for the armature circuit. We can write VDC is equals to this EB plus your IA into RA, and then for the field circuit we have this VDC is equals to IF into RF. Okay, IF into RF, and generally we select the value of RF in such a way so as to have the constant value phi near to the knee point from the flux curve. This is very important point. We have to select the RF in such a way so as to get the flux which is near to the knee point or near to the saturation level, so that we are supposed to have the constant flux for this particular DC shunt motor. Okay, then we know that IF is given by field current is given by VDC divided by RF, because VDC is now connected in parallel with both the circuits, field as well as your armature circuit. Now see, if we have this field current, we are gonna get the flux, and we have set this flux to be the constant. There is no variation in this field current, and we have the constant flux. As we know that, as per the previous discussions on torque equation, speed, then armature current, what we have observed that here what we have is, if I am going to discuss about this particular torque equation, as we know that torque is directly proportional to flux into Ia, like this, and if flux is constant, this torque equation is modified like torque is directly proportional to Ia. You can see over here, because flux is constant in the shunt motor, that's where torque is directly proportional to Ia. If I am going to discuss about the speed, that is given by, speed is directly proportional to Eb by phi, or we can also write like directly proportional to VDC minus Ia into Ra divided by the flux. As the flux is constant, as the flux in this motor is constant, flux is constant, then what will happen? The speed relation now is modified for shunt motor is directly proportional to Eb, okay, or you can say directly proportional to VDC minus Ia into Ra, like that, okay. Now for the third equation, as we get this speed is there, then Ia is equals to VDC minus Eb by Ra. As we are going to put the load on the shaft of the machine, we know that Eb is going to be decreased, okay. If Eb is going to be decreased, accordingly armature current gonna be rise. So accordingly it is going to control the speed of the motor near to its particular previous standard speed, or the depreciation of the speed from its generalized curve, or you can say ideal curve, is the gap is very small, okay. You can say the difference is very small from the ideal speed. That's why this DC shunt motor gives us the very good speed regulation. We have good speed regulation, you can say good speed regulation in the case of DC shunt motor. Now move towards the particular performance characteristics based upon these particular modification in the results. You can see in the next slide. Now you can see over here, first of all I'm gonna draw the torque versus armature current characteristics. This is the first one. As we know that torque in this case is directly proportional to Ia, that's why its curve is like this. You can see over here. Here we have the armature current and here we have the torque, and if we are gonna increase the armature current, accordingly there will be a let me draw again. If we have, just a minute, see here, this is the linear curve, okay. This is the linear curve. As we are going to increase the particular armature current, and after that this curve is bending, okay, like this, due to the heavy load current on the shaft, then its torque is going to decrease, because due to the high amount of your armature reaction, there will be a decrement in the torque also, because the armature reaction is gonna affect your flux in the air gap. Now the second one is the second curve we have between the speed and the armature current. In this case what we have is, as we have discussed in the previous slide about the speed relation, speed we have obtained like directly proportional to back EMF and directly proportional to VDC minus IA into RA. Due to this type of modification in the expression of speed, now the speed for this particular motor, this is the ideal speed, we can say this is the ideal speed, and this is the decrement in the speed, but it approaches near to your particular ideal speed. This is the speed of the motor, and here we have the armature current. This is the reason, because the depreciation of the speed or decrement in the speed is very less, very less. That's why this particular motor is supposed to be the constant speed motor, because the speed is covered by the increment in the your particular torque and the armature current. That's why this speed is regained near to the ideal speed, and that's why this motor has good speed regulation, or this motor can be used for constant speed applications. And the third one is a generalized way of representing the speed versus torque, okay, curve. This is the speed, again this is the torque. Torque is directly proportional to your particular armature current, and this is the ideal level of the speed, and this is the particular curve for the speed as the torque increased on the shaft of the motor. So these are the particular performance characteristics of DC shunt motor. Anybody has the query can ask me right now. If anybody has the query regarding these particular things, performance characteristics of DC shunt motor. Now let's proceed for the next. Now come to the DC series motor. Before discussing the performance characteristics of DC series motor, first of all I want to draw its circuit diagram like this. This is the generalized circuit diagram of DC series motor. In this, and now you have a particular series resistance RS of the field winding. Okay, we have the field winding and its resistance is RS, and we have the armature winding, its resistance is RA, and this is the controlling factor, that is the back EMF. Okay, that is the self-regulating element in the DC motor, whether it is series shunt or separately excited. Now you can see this is the VDC, and this one is the current which is flowing through the IA. As the name suggests, it is a DC series motor. It means all the particular circuits, just a minute, it means all the circuits are in series, means armature circuit, armature, comma, field winding, and your supply voltage VDC are in series, okay. Due to that, our IA, whether we call it IA or whether we call it field current or whether we call it load current, all are same, okay. Now you can represent this from VDC. Suppose this is your load current, and the voltage balance equation for this motor can be represented by VDC is equals to, again, EB is there, plus you can say IA, IL or IF, IA into RA, armature resistance, plus series resistance. And in this way we have armature current like VDC minus EB divided by RA plus RS, okay, like this. Now the main concern about DC series motor is not allowed to run without shaft load, okay, or without load. We can't run this DC series motor because there is a reason behind that. as we know that in the case of DC series motor, it is totally depends upon the flux versus field current characteristics. That is very important. You can see over here, for the DC series motor, we have to take care about the flux versus field current characteristics. We know that in any of the field circuit or field winding, the flux starts rising like this, and it reaches to the knee point, and then it is gets saturated. And we have to mention like this is A, this particular part is B, and this is C. For A to B, there is a rise in flux, okay, or little bit linear manner. But for B to C, it is almost in saturation region, okay, and due to saturation region, flux is considered to be the constant in the saturation region. This is the main concept here. And you can see in the DC series motor, when I call it I field current, it is also the armature current because it is a series winding, okay, and the load current all are same. So if we don't put any kind of load on the shaft of the motor, then our motor's flux parameter is lies in this region of unsaturated. This region is supposed to be the unsaturated region, okay, unsaturated region, and this one is the saturated region. We have to take care about this. How the performance of the speed motor is going to be affected due to this light load condition. Let's come over here. We know that torque is directly proportional to flux into Ia. We will discuss it later. And we know that the speed is what? Speed is directly proportional to Eb divided by your flux, okay, just a minute, Eb divided by flux, okay, this is the flux, or you can say VDC minus Ia into Ra divided by this flux. Now see here, if we are having the light load condition, or we don't put any kind of load on the shaft of DC series motor, what will happen? Its flux lies in the unsaturated region and it is coming back, because as the motor speed is going to be pick up to the higher level, its back EMF also starts rising, okay, back EMF. You can see over here, if the back EMF is rising and flux is decreasing correspondingly, because the armature current is controlled by what? This is VDC minus Eb by Ra. Okay, now you can see from here, if the Eb starts rising because the speed start rising, then this factor is constant, VDC is constant, Ra is constant, our Ia current starts decreasing because there is no load on the shaft. It continuously starts increasing and Ia continuously starts decreasing. Due to that, our flux coming back to the unsaturated region, unsaturated region, okay, and we can't control this speed, and our speed of the motor rises to the dangerously high mode, okay, and the rotor and stator parts may get collapse to each other due to this mechanical vibrations, and motor may get damaged. To avoid such kind of critical condition, we have to put some load on the shaft of the DC series motor. This is the required or necessary precaution to be taken before starting the DC series motor. It must have some load on the shaft, okay, it is connected to some drive as a load. So that's why, because it does not come to the unsaturated region, or an Ia current not should be decreased to the minimum level, Okay, to avoid this condition we put some load. That's why IA is maintained to some particular magnitude, and we can control the speed of the motor up to that extent. So let us move towards the torque equation and speed equation for the same. Now in this case I am taking torque is directly proportional to phi into IA. Now we have two situations: unsaturated region where flux is can be increased to the knee level, and we have the saturated region where flux is to be the near to the constant. Okay, this is the constant flux, and accordingly we have the two case for the torque. If we talk about the unsaturated region, let me write over here unsaturated region, our particular flux torque flux is totally depends upon the armature current, or you can say field current, or you can say load current, like that. And then torque is directly proportional to IA square. So this is the torque equation of unsaturated region. For the saturated region, if we talk about saturated region, our flux is gonna be constant because this is lies in the saturated region, and for particular B to C condition, torque is directly proportional to IA because flux becomes constant. Similarly, speed has two conditions. Speed is, we know that is EB by flux, or directly proportional to VDC minus IA into RA divided by flux. Okay, like this. And for this particular A to B unsaturated region, we know that flux is continuously starts rising up to the level. That's it is gonna be equal to phi A is our particular flux. Okay, now what we have is, now we have the particular speed equation can be obtained. N is directly proportional to VDC minus IA into RE. Now come for the performance characteristics. I'm going to draw over here. If we draw between the torque and IA, this is IA and this is the torque. For the minimum or small values, for the initial values of the current, just a minute. For the initial values of the current, our torque making the parabolic path, and after that it moves like this. For this is for your A to B, and this is for B to C. Why this is almost straight line? Because here we have the saturated region, or flux is constant. Here we have the saturated region. Just a minute. This is your saturated region, and this one is your unsaturated region. Just a minute. Here next we have this is speed versus armature current, And speed versus armature current, we have the speed characteristics like moving like this for the unsaturated region, and after that it is almost straight line. For A to B, this is unsaturated region, and B to C, this is saturated region. And the last curve we have between the speed and the torque like this. And again we have the same configuration for the A to B and B to C. A to B have the unsaturated region, and for B to C we have the saturated region. So these are the performance characteristics of a DC series motor. So if you have any query, any doubt, you can ask me right now. Otherwise I'm gonna end the session for today. Yes, students, any query, or my friends, any query you have, you can ask me. This is all about the saturation region. Thank you so much for watching this video, this session.